Okay. So I would like to introduce Jiwoong Jang, who is in his fourth year PhD program at Wisconsin. He's going to talk about optimal rates of conversion in periodic homogenizations of forced mean curvature flow in the graph setting. Please, you.
Thank you very much for the introduction, and thank you very much for the opportunity. And it's my great pleasure to give a talk. And let me start. Okay, in this talk, we are interested in the propagation of fronts evolving by the normal velocities kappa plus c. Kappa is mean curvature, and c is a forcing term. And this is a periodic function in spatial variable. And the forcing term models the spatially heterogeneous media. And the motivation comes from the motion of a phase boundary moving through a material with heterogeneities. It is derived in Gertin from the computation of energy dissipation that the forcing term is the difference of two work energy, which are determined by the phase and the medium. We would like to see the effective behavior if the environment is periodic. So we zoom out very far away so that the unit cell becomes of micro length epsilon. And now we consider the rescale low. Here we multiply the epsilon to the curvature. So that the epsilon times the curvature can be coupled with the forcing terms, so they have the same status. So if the unit cell has the microscale epsilon, then a radius of like every scale becomes epsilon, so a radius becomes 1 over epsilon. So by multiplying by epsilon, it can be coupled with the forcing term. And now we would like to study the convergence of the moving surface as epsilon goes to 0. And this rescaling is considered in the Croatian and Patakarya, and where for which the two effects they come into play together and they compete each other. And there is another type of rescaling, which is called the parabolic scaling. And for this scaling, please see the paper of Morph and the reference therein. In this talk, I'd like to focus on the hyperbolic scaling I introduced just before. And I'd like to restrict the focus onto the laminar setting, which means the force is independent of a certain axis, which I'm going to take as an x n plus 1 axis. And I'll assume the initial surface is an entire graph in that direction. So looking at the height function of the graph, so we have this initial value problem. So in the big bracket of the first line, we have the epsilon times of divergence. Here the divergence is a mean curvature. And we have also the forcing effect, the C of x over epsilon. And it is known that as epsilon goes to 0, the solution u epsilon goes to u, which is solve the effective equation. So, and I will describe the meaning of C bar. And to describe it, let's look at the formal ansatz. So we formally think of u epsilon as the sum of the macroscopic behavior u plus the character term epsilon times phi of x over epsilon. And here x over epsilon is very highly oscillatory term. And we think of it as a kind of independent scale, which describes the microscopic variable. And we separate the two scales, and we formally proceed the computations. And we take the time derivative, and u of t is similar to u of epsilon of t. And we put the evolution equation, and we then have the right hand side. And if you take a derivative in x, then du epsilon is the du plus the gradient of v. Now we think of the differentiation in y. And then inside we take a differentiation in y, and now it becomes a local problem. And we are now we are taking the second derivative. So the epsilon is cancelled. And we freeze the macro variable x and t as well. And the du of x and t is freezed if epsilon is very small, formally thinking. And if we have a corrector, if we have a solution of this problem, we freeze the direction, and we can solve this kind of problem for every p, then we formally see that the effective solution u solves this equation. And this local problem is called the cell problem. And the c bar of p is called the effective speed. And if you have a solution of the cell problem, then the v is called the corrector. And the spatial part p dot x plus the corrector term is called the almost planar profile. And the combination of the spatial part and the time part is called the traveling wave solution. So looking at a cell problem for fixed p is amount to looking at the flow with flat initial data having that direction. And if cell problem is solved for every p, then it is rigorously shown in the literature by Evans and by classical test function method that u epsilon actually converges to u. And if we have this convergence, then we say homogenization occurs. In this talk, we are restricting our attention to the laminar setting, but let's look at the literature in general periodic media. In the level set case, the Krashen-Patakaria is the first attempt to give a mathematical treatment for non-constant forms with curvature effect. And in Lyons-Sganides, Lipschitz continuous characters were found under this condition star. And this condition star is from the Bernstein method, which is used to derive uniform gradient bound. So, in the paper, this discounted cell problem is considered, and the authors show that there is a uniform. We have uniform gradient bound, so then we can think of the limit. And in this displayed math formula, 1 is used, but if we replace by some small number, this is sigma, then the gradient bound is also uniform in sigma, so we can take the limit as sigma goes to 0, and we can think of this is character for the level set case, also in sigma. Okay. In D. Carly-Ip, the existence of effective is shown under the condition that the C2 norm of the forcing term is small enough. And this is different from the Lyons-Sganides, in that the forcing term can vary sign. In Lyon's scolarities, a C must have a certain sign, either positive or negative, and the oscillation must be very small, according to the magnitude of the forcing term. In T Carly E, the C can vary sign. And it's also obtained by Bernstein method. In Cesare and Novaga, in the laminated setting with initial data, initial graph, which is also periodic, it is shown that there is always a generalized traveling wave solution. Here, generalized means it is not necessarily supported on the entire cell. It may be it's supported on a subset of a cell. So it is always there is a such traveling wave solution. In Caprari mono, without any oscillation condition, if the forcing term has a certain sign but non-vanishing, then in dimension 2, homogenization always occurs. And it is proved in Caprari mono, and in higher dimensions and in laminated setting. Example is provided where the head and tail piece are split, and yes. And in Gao Kim, this systematic study of head and tail piece is provided, and also in the laminated setting, the authors showed that if homogenization fails, then there must be the generalized traveling wave solutions, and supported on disjoint sets. So it's kind of proving the converse part of the Caprari mono of country example is this is because this must be the case. There is traveling wave solutions all the time. And this part is based on the study of Cesarine and Novaga. And now let's look into the literature of quantitative results, which is mostly done for Hamilton-Jacobi equations. Let's first look at the result of Capsuso Zeta Ishii. The authors used the doubling variable method, and they combined with the perturb test function method. And the point is they used phi to the lambda instead of a character phi directly. And this is because we have this bound. And they started the quantitative analysis starting from this bound of phi to the lambda. And if we divide the lambda to the on both sides, then we have 1 over lambda in the right hand side, and that's epsilon to the negative zeta. Here, lambda is taken to be epsilon to the zeta. And as epsilon to the negative zeta is here, so the upper bound is optimized to be the epsilon to the 1/3, and it gives the rate of epsilon to the 1/3 in the paper. And also, in general, we cannot omit this process because in some cases there is no continuous selection of characters as p varies. An example is provided in Mitaketran Wu. Mitaketran Wu started the program of finding optimal rates of a periodic homogenization for convex Hamiltonian. And in the paper, unconditional one-sided optimal rate is obtained, and under some conditions, optimal rate is also obtained. In 2, optimal rate is shown for convex Hamiltonian even with multiscales in 1 dimension under some conditions. In Tran Wu, the authors completed the program of finding the optimal rate for convex Hamiltonian, and they used the curve cutting lemma. They improved the superadditivity of the metric. And this idea is generalized to obtain the optimal rate of time-dependent Hamiltonian in Wu and Tien. And for multi-scale problem, it is recently obtained in the paper of Han and myself. The rate of epsilon to the 1/2 is obtained for convex Hamiltonian with multiscales. And in the paper, the Tran-Wu theorem is used after we fix the macroscopic variable. The idea is after we fix the macroscopic variable, and then we apply the Tran-Wu theorem in each microscale situation with optimal rate. And this idea works for both for Cauchy problem and the static problem. And also this idea corresponds to the separation of scales, because we first fix the macroscale X first, and then we homogenize in Y. So it's a separation of scale. And in a recent study of Mitake Sato, for time fractional Hamilton-Jacobi equations, rate is obtained. In Qian-Tran-Yu, periodic homogenization for viscous Hamilton-Jacobi equations is studied. And now there is a viscous term in the right-hand side, in epsilon times the Laplacian of U of epsilon. And for which the set problem is this. Now we have a Laplacian term. So we have a smoothing effects in Y and P. So we have a nice selection, a regular selection of characters in P. So as we have this regular selection, then we might use the V following the framework of Capsule Docheta Ishii instead of bypassing using fluid to the lambda. So then we might save one parameter, and this turns out to be made rigorous. And this point was previously noted in the AMS textbook of Boom. In the paper of Qian-Tran Wu, on example is also provided where we have this lower bound. So it is justifying the optimality of the rate of epsilon to the 1/2. And in this case, the heat kernel formula is used. In the current setting, the set problem is this for the graph mean Kirchhoff law. And now we are assuming the condition star. So we have a priori uniform gradient bound, and which makes the second order term uniformly analytic. So we can expect the smoothing effects of characters in Y and P, and this can be made rigorous.
Can you explain to everyone what is the tension notations in case people are not used to it? Thank you.
So your theorem is a trace, and this is a Hessian, and this is obtained after the divergence. So after expanding the divergence, this is the sum. So we are taking the trace of the Hessian and this matrix, and then this tensor product is this for two vectors. This is the matrix this matrix. Thanks for the question. Well, are there any questions? Okay,
this is a maybe typo. Divergence of here. Well,
Yeah, and you mean the whole square root, right? Square root.
yeah.
Right.
Thank you for the correction. The entire situation is depending on strongly relying on the condition star, where we use the uniform gradient bounds like every time. I think it's good to introduce the recent study of noncoercive equation, where the situation is entirely different. In Gao Long Xin Yu, this model is studied the propagation of flame front, following the rule of the curvature effect, and now the capital V models the wind from the environment. And this curvature effect is introduced following the empirical model is suggested by Markstein. Now the situation is non-coercive, so we need a completely new idea, and this new idea is suggested by game theory. And by using game theory, we have this bound for V to the lambda for the discontinuous cell problem. Due to the curvature effect, we have only partial reachability, and the partial reachability is compensated by the minimum value principle applying to the flow invariant set. So we have this bound for every two places, x and y. So it proves the existence of effective bonding velocity. In a recent paper by Mitake, Muni, Tran, Xin Wu, they proved that there does not exist the effective burning velocity. The speeds are splitted for shear flows in high V, and that's the case when the flow intensity is greater than a certain bifurcation point, and the authors proved the existence of such intensity point. Okay, now I'm going to introduce the main results, and before that, are there any questions? Okay, okay, here are the main results. We assume the forcing term is C2 and CM periodic, and we assume it satisfies condition star. And we assume the initial graph is globally Lipschitz graph. And we fix the capital T. Then on Rn times the time intervals from 0 to t, then we have this convergence rate between u epsilon to the u. We have the rate of convergence epsilon to the 1/2. That's the statement of the first theorem, and the second theorem is if we take this particular choice of C and initial graph, then we have this lower bound, and this justifies the optimality of the rate epsilon to the 1/2.
maybe for reference, I mean, this is clear. Can you write down a condition star for people to see? Thank
It's
you.
stories. Star is this condition, and here delta is from this. The same delta is from this condition. Thank you for the question. Are there any more questions? Okay. First of all, I'd like to go through the well-positiveness of the equation 1, and after through the change of variables, then we have this equation number 5. And the point is the initial graph has the same Lipschitz constant as u0. So having the global Lipschitz constant is the class of initial data. And we have the well-positiveness over all time. And moreover, we have the uniform gradient bounds over space and time. There might be a blow-up issue from there's a faraway part of Rn, so the solution might blow up in a finite time. So I needed to control the gradient. So to prove that first of all, we show the a priori gradient bound in a short time. We started from the short time existence. That's because we now have a forcing term. So it looks like up to constant. We have this. So if t is a certain time, then the gradient might blow up. So we have a short time a priori gradient bound, and which also proves the short time existence, and we have a priori estimate of higher order tensors, including the curvatures. After this, and we have in a short time, we have the estimate of the gradient and Hessian, and we plug into the equations here. Then at least in a short time, we have the finiteness of time derivative. And after ensuring the time derivatives are finite, then we run the Bernstein method. And then we think of the penalization term, and there is a maximizer, and then maximizers satisfy properties because the time derivatives are finite in this short time. And after proving the bound of time derivative, and after running the Bernstein method with condition star, we prove the gradient estimate. And now this is also uniform in star, uniform in time. And then we can extend the time of existence at least a certain amount, a certain uniform amount of time, and we extend and extend and extend. And we can extend the existence for all time. The gradient is proven to be uniformly bounded over space and time. So only the values in this set are important. So I'd like to introduce the modified force. Here, C tilde is a modified force. The purpose of introducing this modified force is to make the force constant outside of a compact set, so that the set problem becomes trivial. while doing this process, we can keep the list of assumptions still true. We still have the regularity of C2 and C infinite, and we have the periodicity, and in particular, we can keep the coercivity condition. And this coercivity condition A3 prime is used to prove this proposition. For the modified force, for the modified equation, we can find the corrector. We still have the uniform gradient bound due to the condition A3 star, A3 prime. And moreover, the V tilde is regular in Y and P, and also eigenvalues are also regular. And moreover, V tilde is trivial outside of complex set because C tilde is a constant. So therefore, we have this global bound of V tilde, including C0, C1, and C2 estimate, the C2 norm. Changing from F to F tilde does not change the problem because we only use the values of the P less than M due to the gradient bound. So we would like to use this modified operator F tilde. And by doing so, we have the additional property of this global bound of V tilde. And we are going to use F tilde, but by obvious of notations, I will still use F. But now this F has this additional property. Okay, now I'd like to briefly sketch the proof of theorem 1. And to start this, let's look at the formal ansatz. And after differentiating in X, we have this expansion. And here we have the second derivative of U in X, and this is a bad term. U is a solution of the first order problem. And we would like to avoid the direct derivative, the direct second derivative of U. And this is achieved by freezing. So we introduce additional parameter Z, and then we penalize. We make them X and Z are equal. And here I'm using the Japanese bracket. Now we are going to work with this auxiliary function in X, Y, Z, T, S. And there is a maximizer if we fix the capital T. That's because if X and Y are far away from each other, then this term will penalize the whole quantity of phi. And if X and Y are close to each other, then this difference will be close because they started from the same initial data. But the time runs only over up to time t when you are fixing the capital time t. So this will be bounded by some constant depending on t. And now this term penalizes. So there is a maximizer. There is a maximizer, and by plugging in x hat to the place of z hat, we have this relation, and then we will have the difference of x hat and z hat. We can give the upper bound of the difference, and this is that x hat minus z hat is bounded by constant times epsilon. And similarly, plugging in x hat, y hat, z hat by changing places, we have this modulus estimate for x hat, y hat, z hat, and also time part. And we claim that the case when the two times are positive cannot happen for this choice of gamma and k. So to prove this, we suppose not, and we will make a choice after all the derivation. So now t hat is positive, so we can apply the subsolution test. After freezing y hat, z hat, and s hat, this function attains at a maximum at x hat t hat, and now we can apply the maximum principle. U epsilon is a classical solution. So we have this at x hat and t hat. We can directly plug in to the equation to this. And here we multiply epsilon to the Hessians. So we have the cancellation of 1 over epsilon. So we have the Hessian of the character. And the other parts will be very small because this is epsilon, the denominator is epsilon to the 1/2. So it's going to be epsilon to the 1/2, and there are remainders. And for the gradient part, we have the gradient of the character, and this term is similar to this momentum, and we are taking that character associated with this momentum. So after plugging in all the derivatives, we have this, and we have this remainder term, and now with a super solution, so we have this bound. And so now we have an upper bound of f bar by using the fact that t hat is assumed to be positive. And similarly, now s hat is positive, so we apply the super solution test. We need to freeze once more by introducing psi. Due to the same reason, we want to avoid the second derivative. And then we penalize with additional parameter psi and the sigma. And then sigma will be sent to 0. After introducing this auxiliary function, we use the fact that this auxiliary function attains minimum at y sigma and s sigma, and now psi sigma is freezed. So by viscosity super solution test, we have this. And now we send the sigma to 0. And then now we have the lower bound f bar. We connect the upper bound and the lower bound f bar to obtain this. And this happens if t hat and s hat are both positive. And now we make a choice. K is constant times epsilon to the 1/2, and the gamma is less than that. Any less quantity will work. And then K dominates the right hand side, and this is a contradiction. Are there any questions?
Can you explain in a sort of quite sort of like big picture why the proof goes through and everything is clear, right? Can you explain why did you get epsilon to the 1/2, which is better than Capuzzo, Cheta, and Ishii, which is epsilon to the 1/3?
That's because we are using directly the V. For instance, in this estimate of characters, there is no lambda. We are using the direct Lipschitzness of V. But if we use v to the lambda, then we would have this Lipschitz bound. So we need to divide by a lambda. Lambda is very small, and that becomes the quantitative analysis. And now we are not using lambda, and we don't have 1 over lambda, so we only have epsilon to the 1/2. And thank you for the question. Are there any other questions? Okay, for this choice of k and gamma, it must be either t hat 0 or ansatz is 0. Then psi, the maximum value of psi at these hat values is controlled by 0 and the t hat and ansatz, which is also close to 0 with the error epsilon to the 1/2. So we have this bound, and this is a maximum value of phi. So we plug in the arbitrary value of x and t to the phi. And now it obeys this, and we have this bound. And after rearranging the terms, we arrive at this, and the gamma can be arbitrarily small, so we send it to 0. So now we have this one-sided bound. So this proves the one-sided bound. And the other side is also similar. We flip the sign of the tested functions, and we do exactly the same. Now let me briefly describe the proof of Theorem 2. Here I'm taking this particular choice of the force and initial graph. And without loss of generality, I may assume n is 1. So the first is a constant. So we have this effective equation, which now we have a unique viscosity solution. Looks like this. So it looks like a cone. It's going downward with the square root of with the speed square root of 2. If the gradient is smaller than 1, then it will go down with a slower speed. Now is a cone has gradients plus minus 1, so it enjoys the maximum speed of going down. And the initial graph is a scale invariant, and also the environment is a scale invariant. So U epsilon can be solved by this. Here, W solves just a unit scale problem, and through the change of variable, then we obtain the U epsilon, because everything is scale invariant. Now, to compare, we introduce the W bar, which is the solution of the curve shortening flow. It has 2 properties. The first property is the gradient is less than 1 for positive time. The second property is W bar is self-similar. So it evolves like this. From this, we have this one-sided bound. The reason is gradient is smaller than 1. So subtracting square root of 2 times t is like we are playing it down with the maximum speed. So this left-hand side is lies below than the solution w of x and t.
Can you perhaps write down the equation for W and explain this part because it seems important here. Thank you.
W solves this equation. And if we plug in this, if we plug in this left-hand side to the equation, then we have this, and we have this, and this is the W bar of sub t, and this is less than square root of 2. So this is a subsolution. Left-hand side is a subsolution. So we can rigorously check by this. The geometrical meaning is the gradient is less than 1, and actually this is reflected in this computation. And actually this comparison is tight. The reason is if we everything is a scale invariant, so if we zoom out the situation and they see the evolution of curve, then this evolution of curve looks like a cone. So it's asymptotic, like just having gradient plus or minus 1. So it enjoys almost the maximum speed. That's where we get the optimality of the rate. So we have this. We express these zooming out, plugging in this change of variables. And this is the effective solution part, and we recover the U epsilon. And then by the rescaling of self-similarity, we have this. We have the square root of here, and this is used here. So we have this side of comparison. And now we plug in the time equal to 1, and we have a constant. So we arrive at this lower bound. Okay, the analysis is strongly relying on the graph structure. And the next natural question is, can you do quantitative analysis for the level set case? That's the natural question of the next step. And also the interesting question is, will there be a game theoretic proof? And also relate to the quantitative analysis, the regular selection of characters in P was important. And it is of independent interest. This is that is because this is related to the regularity of effective shape, or F bar. So I put the second question as of independent question. So I think these two questions are interesting and important. So I'm introducing them. This is the last slide, and thank you very much.
Thank you. So let me stop recording, and then we can have questions for you. Wait, I have to stop.